It's problem number 19. Very confusingly written. It's got membrane walls of living cells have surprisingly large electric fields across them due to separation of ions. Membranes are discussed in some detail in nerve conduction electrocardiograms. So you can go click there and find out how this physics is related to biology, related to living things. Okay? They ask us what is the voltage across an 8 nanometer thick membrane if the electric field strength across it is 5.4 megavolts per meter. You may assume a uniform electric field. Okay, so how the heck do we do that? They give us some values. They give us a voltage. Well, we need to find the voltage, so V is what we're looking for in question number 19. So I would write down V and do a big fat question mark because I don't know what that is. Across an 8 nanometer thick membrane. So I know this membrane has a thickness of 8 nanometers, which is 8 times 10 to the negative 9 meters. And that's some thickness. If the electric field strength across it is 5.5 megavolts per meter. So the electric field, I know, E is equal to 5.5 megavolts. What's mega? That is million, so that would be times 10 to the 6 volts per meter. So I'm putting everything into SI system. Need to figure out what that 8 times 10 to the minus 9 represents. So to do this, if you clicked on the nerve conduction electrocardiograms and read a little bit about those, you'd be able to draw a little picture of what this is. So this is a membrane wall with some thickness. Okay, so we set up an electric field. I have some, maybe some positive ions up here, some negative ions down here. So if I set up those two little sides of this membrane, that sets up an electric field in between those two little sides of the membrane, the two walls. What direction does that electric field go? What direction do electric fields go? Away from the positives and towards the negatives. So where is this electric field going to go in between here? Is it going to go up or down? Down. It goes from positive charges to the negative charges. Perfect. The electric field goes down, and these are separated by some distance. I think your book uses D to represent distance. Yep. So this would be a D. I think that's what I use too. I use different variables in different classes. This class I think uses D. Yep. So I've got an E, I've got a D. I need to find V. Is there an equation that relates all of these? There is. It's given in the lecture. It's given in the chapter summary, I think. V equals ed. V equals E times D. So I would do 5.5 times 10 to the 6 volts over meters times 8 times 10 to the negative 9 meters. I look at my units and I see the meters are going to cancel each other out. And then when I multiply this out, I should get about 4.4 times 10 to the negative 2 volts. So that's my voltage.
Does the negative charge of negative positive of the answer depend on
Then
the answer is positive 4.4.
yeah,
Could it be negative 4.4?
No. V is a scalar, so V doesn't have a sign that's associated with it usually because there's no direction to associate it with. Technically, since this V is going down, you would assume that would be a negative, probably, but V has no direction because it's a scalar. Okay. Yeah.
What's the variable V stand for?
V stands for voltage, or electric potential.
Yes, that's I have it.
Yeah. So potential and voltage, electric potential, they're all the same. All right, another question that somebody submitted. This is one of the last minute submissions. Problem number 25. So let's see 25. Number 25 asks us, what is the potential 0.53 times 10 to the negative 10 meters from a proton, the average distance between the proton and electron in a hydrogen atom. So I want to know what is the potential from a proton. So proton is just a single charge, just floating around out there. Potential due to a point charge, we have an equation for it. Electric potential due to a point charge. What is the equation for that? Yeah. Yep. K times big Q over R. So K is going to be that constant from your equation sheets. What is your equation sheet listed as? I think it lists it as 9 times 10 to the 9. Yeah. 9 times 10 to the 9. Q. I need to find the potential from a proton. So what's the charge for a proton? 1.6 times 10 to the minus 19. And what are the units on that? Coulombs. Divided by R. The R they gave us is 0.53 times 10 to the minus 10 meters. So you plug and chug your numbers in, and you should find a voltage of about 27.2.
What was the 9 times 9 to the 9? The 9 times 10 to the 9?
That's K,
Oh, yeah.
which has really, really long units. Newton meters squared per coulomb squared.
When you do these, it looks so easy.
Yeah. It is so easy. I have been doing it a long time. That's why they pay me the big bucks. $75,000. Woo! I do. I have fun. It was enough that I could afford to buy. I bought a new TV. It got delivered Wednesday. It's gigantic. I got a 75-inch screen.
What?
Yeah. I have a movie theater in my home. And then I got surround sound too, so I have surround sound all around me. Yeah. And the heat is fixed too, so I have heat now too. It's great. I didn't care about that. I care about the TV. I think this is actually a little bit bigger. I don't know. I need to measure it.
I think it is.
I think this is bigger than 75. My TV doesn't look this big, but it looks nicer. My screen is much nicer. It's fancy. Yeah, sure. Super Bowl party. Nah, I don't watch football. All right, next question that somebody asked. Somebody asked about 61, which I believe is a capacitor problem. And we're going to skip 61 for the moment. And we're going to jump to, I think the other one somebody asked about was 64. Yes, different kind of capacitor problem. In 64, hopefully as PTs you won't have to deal with this, but maybe if you're really, really unlucky. In open heart surgery, a much smaller amount of energy will defibrillate the heart. So when you crack open the chest, you can defibrillate the heart with lower energy. That's what this defibrillator out in the hallway actually does. Did you know that it's a capacitor? So it has two plates, it charges up those two plates, and then when they put it either side of the heart or either side of the chest and they push down, that applies the charge that's on the plates into whatever you're sending it into. Okay, so the capacitor, the purpose of it is to store charge. And that's what they're doing. They're releasing all that charge when they spit it into the heart. Question A asks, what voltage is applied to the 8 microfarad capacitor of a heart defibrillator that stores 40 joules of energy? So to do this, you need to know relationships between energy and capacitance and voltage, and there's a whole bunch of them. You could use any of them. The one that I ended up using, let's write down our variables first. What voltage is applied? So I'm looking for V to the 8 microfarad capacitor. So capacitance is going to be 8 times 10 to the negative 6 farads. And our energy is 40 joules. So energy here is going to be 40 So I need to find some kind of equation that relates all of these. Anybody got an equation that relates all these? I have one that I use, but we can use any other. Shout out one. QVC. Can we use Q equals VC? We're looking for V. Okay, that's good. We have C. That's good. We have E. We don't have Q. So would that be a good choice? Not for now. E equals V squared times C divided by 2?
Yes.
Okay, so that's given in the chapter summary. Let's see if we have all these variables. E, do I have E?
Yes.
Yes, I have E. Do I have V? No, but that's what I'm looking for. Okay, so that's a good thing. Do I know what squared is? Yeah, I know what 2 is, right? The squared number. C, do I know what C is? Yeah, we can see it right here. And we divide it all by 2, which we know how to do. So I can do some algebra on this to get the V isolated. Go ahead and do the algebra to get V by itself. How do we do that? What do we do first? Multiply by 2, both sides by 2. Times 2 and times 2. So we got 2 times E. My 2's cancel out over here. That equals V squared times C. What do I do now? I divide both sides by C? Sure. Divide by C. Divide by C. And those will cancel out. And I get V squared equals 2 times E divided by C. What do I do now? Take the square root. Square root. V equals 2E over C square root. So now I should be able to plug and chug my numbers in, right? Square root of 2 times 40 joules. All divided by 8 times 10 to the negative 6 farads. Plug those numbers into your calculator. You should get about 3.16 times 10 to the third joules per farad. What is a joule per farad? Volt? Are you sure? What should it be? Volts? It is. I need more voltage. What should it be? This is a V, so what should the units on it be? Volts. So a joule per farad is a volt. Okay? So voltage is 3.16 times 10 to the third volts. Okay, and then part B. Part B asks us, find the amount of stored charge. What's the variable for charge? Q is charge. What equation can I use? Q equals VC. Home Shopping Network. Did anybody use QVC as a, do you even know what QVC is?
Yes, it's the home shopping.
Some of you know what, okay. I don't have cable anymore, so I have no idea. 3.16 times 10 to the third times the capacitance, 8 times 10 to the negative 6. Multiply those together, you get 2.53 times 10 to the negative 2. What are the units on the charge? Yeah, coulombs. This is why we teach electricity in the winter, because of coulombs. Heyo. Okay, any questions on that one? No? Okay, we are going to take a quick look. I'm not going to do the whole problem. I'm going to show you a general approach on how to solve problem number 61, which is find the total capacitance of the combination of capacitors shown in this figure.
parallel, so that means you just have to,
So here we go.
yeah, it's just C1 plus C2 plus C3.
Alrighty. This is C5. This is C6. This is C4. This is C3. This is C2. This is C1. Okay. This is a mess. We have to combine all of these capacitors and figure out what all this means. Yeah. So what I do with these, I never try to do it in one step. I always break it down and do it step by step by step. You should get used to using lots of paper and solving physics problems. Don't try to cram all your answers into just tiny little spaces, right? Get used to taking up lots of paper, okay? If you cram all your stuff into tiny little spaces, fine on your homework, but when you start doing that in exams and I can't read it, then I can't give you partial credit, okay? Just a little tip. All right, so I got to start combining these capacitors. I see some that look like they're easier to combine than others. Right? This first branch right here, I can see these follow run right after another. So these two are in series. So I would add these two in series to each other.
They're parallel.
C5 and C6 are in series. When you're going through if you go through a capacitor and the only choice you have is to go through the next capacitor, they're in series. Okay? So C5 and C6 are in series. How do I add capacitors in series?
One over this capacitor, one over C1 plus 1 over C2.
1 over each of the capacitances. Okay? So I would combine these two together into a new capacitor that we're going to call, maybe I would call it C56. So I would redraw this picture and I would figure out 1 over C56 equals 1 over C5 plus 1 over C6. And what you have to remember to do, and I'm going to write this down, I call this flip-flop. After you plug this into your calculator, you have 1 divided by C56. To get C56, you have to flip it. You have to take the reciprocal. So don't forget to take the reciprocal of this.
It's just C of 1.
Raise this to the negative 1 power. Whatever you get here, put it up to the negative 1 power, or 1 divided by whatever you get here.
Yeah.
Okay? So you need to flip that. And then you'll get a C56. So this is what your picture would then look like. There's C4, C3, C2. So I've simplified these two into just this one. And then I look at my circuit and I see this one is parallel to this one. And so I can add those two in parallel. Then I see this one is parallel to these two. But these two, they're in series with each other. But I can't do those yet because this is in parallel with this. So to simplify this even more, I can combine C1 and C2 that are parallel with each other, right? So then it'll give me a new picture. So how do I add those two that are in parallel? Just straight up add. So I would do C12 is equal to C1 plus C2. And then my new picture looks like this. C56, C4, C3, C12. Okay. See how I'm breaking up the capacitors each step? Yes. How did I know to combine these two? because as I'm going through, I can see I can add this one. I can straight just add those two in parallel, right? And I can come to this and I can look at that. Oh, these two, there's two different ones here. So I can't just add those in parallel with these two. So I need to do something with these two. I know I need to combine these two. But then I look at this one. Oh, this one, I can't just combine this one with this one because it's in parallel with this. So I need to simplify this side. Does that make sense? That help? So I combine these two together. Now I've got it down to this. Yeah? So how do I simplify this? I can add this one and this one in parallel. Great. And then I could add this. These two are in series. So they're not entirely just in parallel with these other ones. So I have to combine these two now. I got these into one. So I'll combine those two. How do I combine those two? 1 over. Yep. And I would call that, let's see, 1 divided by C1, 2, 3 equals 1 over C3 plus 1 over C1, 2. And I need to make sure that I flip this upside down. And then my picture looks like C5, 6 and C4 and C1, 2, 3. And then how do I combine these? Just straight up add them. So C total is C5, 6 plus C4 plus C1, 2, 3. And then I have 1 capacitor. Okay? If you follow this procedure, then you can do more complicated questions where we might ask you to solve what's the voltage in every capacitor in the circuit and what's the charge in every capacitor in the circuit. Yes?
Can you explain again how to identify
Parallel versus series. If you're going through the circuit and you have a choice of different branches you can take, then these things are in parallel with each other. So if I come into this circuit, if I imagine I'm coming from up here, I come in, I can go left, I can go through C5, 6, I can go straight down through C4, or I can go through C1, 2, 3. No matter what, I can choose any one of those. I'm not forced to go through one after another, so they're all parallel. Whereas if I go up a little bit, I can come down. Okay, let's come down from the top, and I have different branches I can take. I can go down. I can go through C5, 6, okay, and that's it. And I can go through C4. I can go through C3. But if I go through C3, then I'm automatically forced to go through C1, 2. So if I'm forced to go through one right after another, then they're in series with each other. Okay. It takes a little bit of practice, and these are worth practicing because this is going to come back. The same approach comes back with resistors. Except the adding approach is slightly, just a little bit different. Same theory, same concept, just a little bit tweaked. Okay? Worth your time to get good at doing these. These are kind of things that appear on these things. Any questions on that? If you can see what you have to do, then you can do it all straight away. The only trick is I might ask for like voltages and in between steps, which isn't quite as easy to do if you jump straight to these. But yeah, absolutely, if you can jump straight, go for it. Any other questions? So I can stop recording?